In this video, you will hopefully see the connection between the tools that we have used to study chemical reaction, the kinetics of chemical reactions, with its application to study the kinetics of radioactive decay. The reaction is still the same, where N, and N in this case is going to be the number of radioactive nuclei, become products, whatever they are. Okay. First of all, to indicate radioactivity, you will see in the literature that there's different sets of units because radioactivity has been applied to many areas. Nuclear power plants and medicine, of course, it's also used. In chemistry, is used as well. The SI units, the International System Unit, is called a becquerel, and spelled as BQ, and by definition, it's the 1 nuclear disintegration per second. So the SI units of nuclear decay is number of nuclei per second. If for any real application, this number is huge. So sometimes you will see other units that are not SI, but if the community accepts it as a good unit, as long as everyone agrees, the conversion is somewhat easy. In chemistry, it's also very common to use a curie. A curie, by definition, again, is the number of nuclei disintegrating each second in 1 gram of radium-226. And Marie Curie was studying radium and francium, for example. She is one of the discoverers of radioactivity and its applications and the mechanism of radioactivity, as you well know. The main equations that we are going to study are a first order equation. In this case, we will define the rate. The rate, again, is specified in, if you will, in becquerel or in curies, which has number of nuclei per second, and we say that it's proportional to the initial amount, or it's proportional to, not the initial, whatever the number of nuclei, radioactive nuclei you have at that point. Notice that there's a 1 in here, therefore this is a first order kinetics, so the equations that we get are all very similar. They're exactly the same. Instead of concentration, we have just number of radioactive nuclei. These are N0 is the number of nuclei that you had at the beginning, and at any given time, depending on the constant of the composition of nuclei, is you can obtain the number of nuclei at that specific time. And we can also define the half-life, and in radioactivity, it's very common to refer to the capacity for a nucleus to decompose using its half-life, because that's probably what concerns us the most, is how long will that radioactive material will be emitting radioactive radiation. Sorry for the redundant of the word. Okay, but so let's study a specific application in a health science degree. I'm sure you are very aware that radioactivity is used, of course, for cancer treatment and radiation, but it's also used very commonly as medical tracer for imaging. And you can put in the body fluorine-18. It's not poisonous, at least in small doses, and its radioactivity is not very damaging, but it's used for imaging so that you know where the vessels take that fluorine, so you can take a picture like this one on the slide. So in this case, we're given a specific kind of set of data, and we're being asked how much fluorine you'll have, fluorine-18 you'll have after 3 hours. So let's read the question. It says that fluorine-18 has a half-life of 183 hours. That means that every 183 hours the amount of fluorine-18 is being halved. So if initially you have injected this much in the patient, well, the question is, after 3 hours, can this patient go home? How much fluorine-18 will have in its body, because it has not decomposed yet. We can use the same first order reaction, knowing that, well, we're given the half-life, so K will be logarithm of 2 over half-life. Okay, so how many milligrams you will have? And the initial number of milligrams that we have put in the patient is 285 milligrams. So that means that our result will be in milligrams. Exponent of K is logarithm of 2 divided by half-life, which is in hours, times the hours after 3 hours. 3 hours. Notice again that 3 and the hour and hour will disappear. If you calculate this, you'll see around 1.914 milligrams. So this is the solution. Okay, so as you see, the set of equations are the same. Now instead of concentration, we talk about number of radioactive nuclei, or in this case milligrams. It doesn't matter because to convert number of nuclei into milligrams or grams, the proportion would be the same. So as long as you're consistent with the units of N and N0, you can use number of nuclei, milligrams, kilograms, or pounds, if you will.